Next, I want us to look at how to evaluate definite integrals, which have specific limits of integration using the trigonometric substitution. So let us start with this example here. So first, we need to recognize which trigonometric substitution to use. For that, note that there is no radical written explicitly in this expression, but of course it's very badly disguised right here in the denominator. So we have x cubed, and in the denominator we have effectively 4x squared plus 9 under the square root and then raised to the third power, like so. So, as a matter of fact, this 2 in the denominator of the exponent gives us square root, which is then raised, cubed. All right, now let us look at this expression closer. Which trig sub should we use? If we inspect our table for the substitutions, we see that if we had an expression of the form x squared plus a squared, we'd have to use x equals a tangent theta. Now here, we don't really have x squared plus a squared. We have an additional factor in front of x. How do we deal with that factor? Well, whenever you have a factor in front of x that you want to get rid of inside an integral, one thing to do is to factor out this constant, first outside the radical and then outside the integral altogether. So the way you can think of this is that you have an integral in which in denominator you have, once you factor out the 4, you have x squared plus 9 over 4 under the square root. And then 4 comes out of the radical as 2, which is then raised to the third power. So I want to take 4 outside the radical. I just did this. So I factor out 4, but it's square root. So 4 comes out of 2 from the square root. And then I'll have 2 here inside the parentheses. So the 2 must be raised to the third degree. So it gives me 8. So I have 8. And then these 3 factors of the square root, like so. And then I can take the 1/8 outside the integral altogether. All right, perfect. And so with that, I'm all set. I have square root of x squared plus 9/4. I have x cubed here and then dx, like so. And so this now has the correct form. I recognize it as the substitution, as the expression x squared plus a squared. So that requires setting x to be a times tangent theta. So in this case, a is the square root of 9/4. So think of this as 3/2 squared. That gives you the expression for a, and so a must be 3/2, like so. And so accordingly, I'll have 3/2 secant squared theta d theta for dx. An additional thing that I have to do in this integral is changing the limits of integration for theta. So I have to go from limits of integration for x to limits of integration that involve theta. And so the idea is that I have to solve, so basically my limits of integration here are this form. I have x1 and x2. x2 is 3 square root of 3 divided by 2. And so it must be mapped to a value of theta, like so. So this value of x is obtained as this expression evaluated for some theta, and we have to find the theta. So this is 3/2 tangent of theta 2, and x1 is equal to 0, which is 3/2 tangent of theta 1. Right? So this second line gives us immediately that theta 1 is 0. So the lower limit of integration in terms of theta is going to be 0, as well as the one for x. Now for the upper limit of integration, we have to solve this equation here. And so if you multiply both sides by 2/3, you'll get that tangent of theta 2 equals square root of 3. So if you think about which angle gives this value, so I'll let you think about it for a second, you will realize that theta 2 it must be pi over 3, because tangent of pi over 3 is precisely square root of 3. So now we have converted the limits of integration into those for theta. It remains to integrate everything else in this integral to be in terms of theta. So let's go ahead and do that. So in the integral we have x cubed, which is replaced now with 3/2 tangent theta. It is cubed, and then I have in the denominator I have square root of 3/2 tangent theta squared plus 3/2 squared. So of course that's the point of introducing the substitution, so that we have tangent squared plus 1 once we factor out the 3/2 squared, and this entire thing is cubed. And finally for dx I have another factor of 3/2 secant squared theta d theta. Great. Now let me simplify this integral as much as possible, and then I can go ahead and evaluate it. Let's see what we have here. I can first take care of the denominator. The denominator, I have 3/2 squared times tangent squared plus 1. So that leaves me with square root of 3/2 squared times secant theta squared. So that's my radical there. It is cubed. And in the numerator, I have simply 3/2 cubed times tangent theta cubed, multiplied with 3/2 secant squared theta d theta. Note that once the square root cancels with the square, I don't need to do anything for absolute value as usual, because of the correct choice of the range. So I'll simply have 3/2 secant theta cubed, and 3/2 tangent theta. I guess I can just join these two factors together and write them like so, cubed in the numerator, times 3/2 secant squared theta d theta. The nice thing about this product is that 3/2 cubed and 3/2 cubed cancel, and I can write this as I can take 3/2 from the second factor outside the integral altogether. So I'll have 3/16, then my integral from 0 to pi over 3, and then I'll have tangent cubed theta. Instead of dividing by the entire secant theta cubed, I can cancel this secant theta with 2 factors from the denominator. So that will leave me with a single secant theta, d theta. Now, the good part about definite integrals is that once we evaluate it now, we don't need to change back to x. Once we evaluate it to a number, that is it. That will be our answer. We don't need to change back to express it in terms of x, because that's going to be a number. It's the same regardless of whether you think of it as definite integral in terms of x or definite integral in terms of theta. So now it remains to evaluate this definite integral. It's a trig integral, so we know what to do. So in order to be able to evaluate it easier, we have two options. We can either think of it as, so this is an integral which involves product of powers of tangent and secant, or we can transform it to product of powers of sine and cosine. So you get to pick which you like better. I think I'll go with product of powers of sine and cosine. So I will take this product and convert it to sine and cosine, because I don't like to deal with negative powers. But in principle, you could do that just as well. So what I will do with this expression is I will rewrite it as, so I'll use that tangent is sine over cosine, and it's going to be cubed. And then since secant is 1 over cosine, I'm multiplying by another cosine theta. Okay. So that I now have 3 over 16, 0 to pi over 3, sine cubed theta over cosine squared theta d theta. All right, and so this now has again the form of a product that involves negative powers. So I don't have any choice but to go ahead and evaluate it. So I couldn't get rid of the negative powers. So let me see what else I can do. Note that I have an odd power of sine and an even power of cosine, right? So I can use the u sub that is appropriate for integrals, for trig integrals of this form. So remember, whenever I have an odd power of sine and an odd power of cosine, I want to take one of the sines and use it for the du. Now I could have looked at this previous expression I had here and think of it as, well, again, this is a product of an odd power of tangent with an odd power of secant, and I could have used secant tangent for du. So that was another possibility. I could have treated this as a trig integral with secant and tangent, but I'm somehow more comfortable with sine and cosine, so that's what I'm going to use. I'm going to say now that I guess even before that, I want to rewrite it slightly. So what I will do to it is I'll take sine squared and express it as 1 minus cosine squared theta. Then I'll have another factor of sine, and then my denominator will be cosine squared. All right, like so. Now I'm ready to actually introduce the u. I will let u to be cosine theta, and then du is of course minus sine theta d theta, so that's almost exactly what I have here, up to the minus sign, of course. And then I'll have minus 3 over 16 integral from 1 to 1/2. Here I have 1 minus u squared. Then I have minus du, but I already put the minus out front, so this will be just du. And denominator is u squared. Okay, perfect. Now this is a straightforward integral to evaluate. So I have it as 3/16, 1/2 to 1, integral of u to the minus 2 minus 1 du. So that's perfect. This is simply 3/16. Here I have to write u to the minus 1 divided by minus 1 minus u, and this must be evaluated from 1/2 to 1. So to integrate u to the minus 2, I incremented the exponent and divided by the new exponent. The usual procedure for integrating power functions. And now it remains to just put in the variables, put in the values. And so here I have minus 1/u minus u, and I have to take it from 1/2 to 1. So that's, let me see, this is 3/16. I have minus 1 minus 1. Then I have to subtract the value for 1/2, which is minus 2 minus 1/2. So that's 3/16 minus 2 plus 3/2, suppose. And I have minus 3/32 as my answer. Yeah, except that, whoops. Except that I have to actually add 5/2 and not 3/2 here. Whoops. So that that just changes the sign here. All right. So it's not minus 3/32, it's plus 3/32. That's because I have minus 2 here, and then I'm adding 2 and 1/2 in the second term. And so this is 3/16 times 1/2. Right, so again, fortunately for us, this is just a number. It doesn't need to be changed to x or anything, so that is the final answer here, 3/32. Now, let's summarize what we had to do here. So it was relatively straightforward to pick the right trig sub once we had the radical exposed. So one thing that you have to keep in mind is powers like these can be written as powers that involve radicals, square roots specifically. Another thing is whenever you have constant factor times x squared plus constant squared, you can take the coefficient in front of x outside the integral, and then you're in the case where you can apply trig sub directly. So whenever you have some coefficient that gets in your way next to the x, you can take care of it by factoring it outside the integral. So this is the main takeaway of this example, as well as that for definite integrals, you really just need to evaluate the definite integral in terms of theta. You don't need to change back to x. So that is the moral of this example.